an improper integral is a definite integral where there's something that's a little bit off. Either the function's not continuous everywhere in the interval for the integral, or one of the bounds is an infinity. And how does that even make sense? So what do I mean by the first case? Let's say we had an integral from -1 to 1 of 1 over x dx. Now, since we're going from -1 to 1, the problem is this isn't defined at 0, and 0's in this interval. So this would be considered an improper integral. Or if we were to say we were integrating from 0 to infinity, x squared e to the x, who knows, something like this. In this case, here we have one or both of our bounds could be, but at least one of our bounds is at infinity. Now what makes this tough, because remember what we do is when we integrate this, we end up with some function, and then we have to evaluate it from 0 to infinity. Well, the problem with these is how do you plug in an infinity, right? Because remember, infinity is not really a number. So we're going to see how to take care of this case. We're not going to look at this case this semester, but we are going to take a look at the case when we have infinity as one of our bounds. So here's what we're going to do. If you're given an improper integral, and let's say we're just going from a to infinity of some function dx. Well, since we can't plug in an infinity, what we're going to do is we're going to turn this into a limit. We're going to say, let's let the limit as some letter, most books use b here, I don't know why, as b goes to infinity from a to b f of x dx. Right? See, now we could go ahead if we wanted to, we could integrate this. And remember, just kind of the notation, if we integrate little f of x, we get some other function that we generally call big f of x. We'd evaluate that from a to b. So this would be the limit as b goes to infinity, top endpoint minus the bottom endpoint. Now remember, these are just some functions, so now we're just back to doing a limit like we did at the beginning of the semester. So basically all we're going to do is we're going to integrate like we normally would, but we're going to replace our infinity bound with a letter and then take the limit as that letter goes to infinity. All right, let's try a couple examples here. So the directions here would just be integrate or evaluate. And let's say we did the integral from 1 to infinity 1 over x squared dx. Nice easy one. All right, now first off, you can see that this thing is improper because we have a bound at infinity. Now this thing is continuous from 1 to infinity, right? This is only discontinuous at 0, so that's not a problem. But since we're going from 1 to infinity, the first thing we want to do is go ahead and turn this into a limit. The limit as b goes to infinity, the integral from 1 to b, 1 over x squared dx. Okay, now we're going to treat it like any other integral that we do. So this is going to be the limit as b goes to infinity. I'm going to rewrite this so I can integrate it. I'm going to write that as x to the -2 dx. All right, so let's go ahead and integrate this. The limit as b goes to infinity. Add 1 to that power, we get x to the -1. Divide by that new power, -1, and we got to evaluate that from 1 to b. All right, I'm going to move this up top and kind of simplify what we have here. The limit is b goes to infinity. If I rewrite this, that's just -1 over x evaluated from 1 to b. Okay, top endpoint minus the bottom endpoint, so limit as b goes to infinity. This is -1 over b minus -1 over 1, or the limit as b goes to infinity, -1 over b plus 1. All right, now that we've simplified that, we need to take the limit as b goes to infinity. And we can see here, in this case, since we only have a b in the denominator here, the denominator is getting bigger and bigger and bigger, the top's staying the same, which means this right here, this is heading off towards 0, right? That's getting smaller and smaller and smaller as b gets bigger and bigger and bigger, which means the answer to this is just 1. Now we generally say, we haven't used this terminology before because we didn't need to, but if a integral adds up to a finite value, we actually say that this integral converges. Every integral that we've done with bounds so far has converged. If it doesn't add up to a finite value, say it runs off to infinity, we actually say that it diverges. All right, let's take a look at another example. Let's do one that's really, really close to this. Let me grab an eraser here. Let's change this up just a little bit. What would happen if I just write this as just 1 over x dx? All right, well, most of our steps along the way are going to be exactly the same. This is still an improper integral, so we're going to go through all those steps. We're going to do the limit as b goes to infinity, 1 to b, 1 over x dx. Then we're going to integrate this. Well, this is already in a form that we can integrate. That's our logarithm, so this is the limit as b goes to infinity, the natural log of the absolute value of x, evaluated from 1 to b. Top endpoint minus the bottom endpoint. So we do the limit as b goes to infinity, the natural log of the absolute value of b minus the natural log of the absolute value of 1. All right, we can simplify this a little bit before we actually take the limit. If you remember from your pre-calculus days, the natural log of 1 is actually 0, so this is really just the limit as b goes to infinity of the natural log of the absolute value of b. Okay, so what happens to the natural log function as the values that you plug in get bigger and bigger and bigger? Well, it may be helpful if you remember what the graph of the natural log looks like. It has a vertical asymptote right here at the y-axis and looks something like that. So what's happening to the y values of this graph as we get bigger and bigger and bigger? Well, it's going up really slow, but it's still going up forever, which means this is infinity. So this did not add up to a finite value, so we'd say that this integral diverges. Okay, so if the integral adds up to a finite value, we say that it converges. If it adds up to an infinite value, or not a finite value, of course, it diverges. Let's take a look at maybe one more example here, just to kind of show you the type of things you might run into. Let's say we're integrating, let's go 0 to infinity, 3e to the negative 5x dx. All right, again, when we're taking a look at this, we can see it's an improper integral because we have a bound that's an infinity. This function is continuous from 0 to infinity, so that's not a problem. But we do have that infinite bound, so the very first thing you want to do, let's go ahead and change this into a limit. The limit is b goes to infinity, 0 to b, 3e to the negative 5x dx. Okay, now we can just worry about integrating this. Now remember, the 3 here is a constant, so we could actually pull that out if we wanted to. The integral, remember, the integral of e to the negative 5x dx would be negative 1/5 e to the negative 5x. So when we do that, let's see, that's going to give me the limit as b goes to infinity. We already have a 3 out front, so that's negative 3/5 e to the negative 5x. And we want to evaluate that from 0 to b. All right, like always, when we're evaluating a definite integral, the top endpoint minus the bottom endpoint. So the limit as b goes to infinity, the top endpoint, 3/5 e to the negative 5b, minus negative 3/5 e to the negative 5 times 0. All right, before we go too much farther, let's see if we can, clean this up a little bit. So the limit as b goes to infinity. Since this has a negative exponent, I'm going to go ahead and write this first piece as negative 3 over 5e to the 5b. Minus a negative becomes a plus. This is going to be e to the 0. Anything to the 0 power is 1, so that's just 3/5. Okay, now that we got that about as simplified as we can get it, let's see if we can evaluate this limit. Well, this is the only thing that has a b with it, so what's happening to this as b gets bigger and bigger and bigger? Well, exponentials get bigger and bigger and bigger, so the denominator's growing exponentially, so really, really fast. The top's a constant, so this is actually heading towards 0. So as we take the limit, this is going to 0 plus 3/5, open up, which would be 3/5. So since this added up to a finite value, we could say that this integral converges. Okay, so improper integrals, the ones that we're going to take a look at this semester, are going to have an infinity at one of the bounds. Replace infinity with the letter and do the integral, then let the limit as that letter heads off to whichever infinity you're dealing with. Not too bad, just we're adding one extra step into our integration process.